So for today, I'm extremely pleased to have my friend Themis Sapsis from MIT to come to give us a seminar on a very busy week, all the way from California and on the way to Boston. So Themis is an associate professor at the Mechanical Engineering Department at MIT. I think it would be fair to say he's a rising star on all aspects of UQ and dynamical systems. He has received basically every single award that exists on young investigator type of things. He's a graduate of my own National Technical University of Athens. He did his PhD at MIT. He has been a postdoc at Recurrent, and he's currently in the Faculty of Mechanical Engineering, and he's going to speak on prediction and quantification schemes for extreme events. Before I ask him to proceed, he really needs to leave sharply at 5 o'clock, so he will make an effort to stop maybe 10 minutes before 5, but don't try to catch him at 5 because there is a Uber guy waiting for us to catch, okay? So 5 p.m., sharp is out. And with that said, all yours.
All right, thank you. Thank you very much for the very nice introduction, and thank you for the invitation. It's a great pleasure to be here. And I want to discuss today with you, to present you some recent results that we have on the prediction and understanding of extreme events. This is joint work with two members of my group, Dr. Farazmand, who is a postdoc, and Zhongyi Wan, a senior graduate student. And also in one aspect of the problem, we have collaborated with Dr. Patrick Bloningen, currently a NASA postdoc. So before I start to the main discussion, I want to first give you an informal distinction between what we call rare events and extreme events, right? So first of all, an extreme event, informally defined, is a large deviation from normality. In reality, what we have is some sort of stochastic attractor, right? Some statistical steady state, and these extreme events are transient that basically kick the system away from the main attractor. So what is the difference between rare and extreme events, at least in this context? A rare event is basically something that it is a low probability event, right? Winning the lottery, just a combination of numbers. Nothing special about it. It's just a very, very rare event to happen. On the other hand, extreme events, when we talk about extreme events, we basically refer to something that involves the synergistic action between dynamics and stochasticity and a low probability event. So this is important because, as you will see, extreme events, they tend to occur much more often than a rare event out of a Gaussian distribution, okay? So again, when we talk about extreme events, we basically have in mind a dynamical mechanism in mind. This can be an instability of finite duration, some sort of self-organized criticality, a feedback loop, etc. So in that sense, extreme events is basically a subset of rare events, since they involve both a probabilistic perspective but also a dynamics perspective. So let me give you some motivation. This is what I call wave turbulence, basically rogue waves that arise due to nonlinear focusing. And here is an old footage of an aircraft taking from an aircraft carrier. And you see the surrounding seas, they are not really bad. And then all of a sudden, we have a wave at the wrong moment, okay? The plane actually made it. That's the good news. The only reason the plane made it is because it has propellers, okay, not turbo jet. So diesel engine and propellers, very reliable. But the emphasis here is that this is an aircraft carrier. We're talking about like 50 to 55 feet deck, right? This is a pretty high deck, and still you can see the wave out there. So, well, what is the mechanism here? Going back to the picture I described you before, as you know, water waves is a dispersive medium, right? So wave groups of different size propagate with different velocity, and that naturally creates some mixing of phases, okay? So dispersion is the mechanism that creates the mixing of phases, and on the other, so that's the probabilistic aspect. And on the other hand, we have the mechanism modulation instability, which is a nonlinear mechanism, and certain wave groups that they randomly form out of this dispersive background, they basically magnify even further because of nonlinear effects. So here you see the mixing of wave groups that propagate with different speeds, and then a critical wave group is formed, and this wave group, it undergoes modulation instability, and it gives you this rogue wave. Well, this is again for unidirectional weak non-unidirectional waves, and this is manifested by direct numerical simulation. So if we go and simulate full water wave equations, this is Gaussian theory, the dashed line. So this is the PDF of the wave elevation. Okay, that's in the logarithmic plot. This is Gaussian, and this is what we actually get. And the only reason to get the non-Gaussian tail is because a nonlinear mechanism is involved. Otherwise, if it was a purely linear phenomenon, we would be talking, because of central limit theory, for a Gaussian thing. So another example is, well, a very basic or prototype system of turbulent behavior. We basically consider, we will talk more about it, we'll consider Navier-Stokes equation defined on a two-dimensional periodic box with constant in-time forcing over just one Fourier mode. This is the well-known Kolmogorov flow. And if we plot the probability density function for the dissipation of the flow, you see we have this core of probability, and then we have this tail that is essentially associated with these intermittent bursts of dissipation. So most of the time, this is the dissipation over time. Most of the time, dissipation fluctuates around a fixed value, and then in random instances, we get these bursts of dissipation, which are pretty, well, people have spent a lot of time and effort to analyze the dynamical mechanism, but it's not really easy because it involves many multiple steady states, traveling waves, periodic orbits. These steady states are not necessarily stable, so they're even hard to compute. So the question is if we can predict those, right? So there are two goals that we are exploring. One is to derive precursors. So we're taking a different approach. Instead of trying to solve the equations forward in time and do filtering or data assimilation, we're trying to derive precursors of these extreme events. In other words, characteristic patterns that precede these occurrences. And then on the second part of this talk, I will talk a little bit about how to formulate combined equation-driven and machine learning schemes to describe exactly, to basically develop reduced order models for these extreme events. So the systems that we have in mind and the challenges associated with them, we're basically thinking of systems that are characterized by an attractor, by some statistical steady state. This attractor is represented here as this blue sphere. So think of this blue region as the region where the system spends most of its time fluctuating randomly, and then because of certain instabilities, we have these rare transitions indicated with the red trajectory. So we're talking about essentially nonlinear dynamical systems with positive Lyapunov exponents that create this sort of finite size attractor, and then intermittency, right? We have finite time instabilities that lead to these rare transitions. It's hard to solve this problem with large deviation theory. And the reason is because these are very high dimensional problems, okay? Large deviation theory is limited to systems perturbed with weak noise, and usually the applications that at least I know, they're restricted to low dimensional cases. So, known mechanisms for extreme events. We have extreme events arising because of slow manifold dynamics. So if there is a folding in the slow manifold, then we can have these rapid transitions that involves multiple scales. We have a transition path theory that examines, which is basically very close to large deviation theory in the sense that it examines systems where these rare transitions are triggered by noise. And then we have heteroclinic cycles, a more deterministic situation. where again, you have a very nice and low dimensional structure in your system. The problem is that as the complexity rises from a low dimensional system to high dimensional systems, as the ones that I show you, the tools need to be either reconsidered or completely redeveloped. Okay, so I start with a prototype system for extreme events. This is a dispersive wave model, and it's the Maida-McLaughlin-Tabak model. What this is, so you can think of it as NLS, nonlinear Schrödinger equation. This is the nonlinearity that we have, focusing nonlinearity. And then we have the selective Laplacian term. This is basically dissipation acting only on very small scales, okay? And then we have this dispersion term that is basically, it's a pseudo-differential operator associated with deep water wave dispersion, all right? So you don't really need to understand everything about this equation. What I want you to focus is the fact that this equation gives extreme events. So this is space and time. This is a simulation. And if you watch very closely, you can see that out of nowhere, you have this very, very purple regions associated with extreme events. If you cannot see it very clearly from here, you can observe the spatial maximum over time, and you can see that most of the time the spatial maximum, it fluctuates around a given value, and then over certain instances, it creates these spikes. The same thing can be seen from the probability density function, where again you can see the Gaussian core that is associated with linear dynamics, and then you have these heavy tails associated with these very sudden peaks, okay? And the question is, can we predict those? So, the standard thing that people do in this case is stability analysis, right? We take a solution of this equation, a periodic solution, and we do the stability. This has been done many, many years ago by Benjamin Fair. This is the well-known Benjamin Fair instability. And you see that for a certain amplitude, if it's sufficiently small, we have a stable solution. If we exceed this, then we get this very, very sharp solution that is associated with energy cascade to small scales. That's why we put the selective Laplacian, the dissipation, so that we stop this sort of cascade to smaller and smaller energies. Now the question is, okay, we characterize what is unstable in this case. The question is how useful this is, okay? And the reason I'm asking that is because you see these are global solutions. On the other hand, the extreme events that you see here, they're very localized, all right? So in this sense, we decide to consider localized solutions of this form, okay? And you see we have a constant background, B, and then some amplitude C, and an exponential, a Gaussian initial condition localized over a length scale L. Now, let's see something carefully. What this surface does is to separate initial states that tend to grow from those that basically diffuse and disappear. And what I want you to emphasize, to see is that as we change the length, the initial length scale of the initial condition, you see there is a critical point below which nothing grows. Okay, this is no surprise given that we have incorporated selective damping. So below the selective damping, below the scale of the selective damping, it is natural to expect that nothing will grow, and this is what we see. On the other hand, if I go to the case of, this is B, B is the background energy. If I set this B equal to 0, then I see that the more localized the initial state is, the easier, meaning with smaller amplitude C, it becomes unstable. Okay, but this should not continue to really, really small and localized states because there is this selective Laplacian. The end story is that there is a critical length scale, this problem. Okay, and this critical length scale, it's here, it's basically the length scale associated with the perturbations that need the minimum amount of energy, a very small amount of energy to grow. So instead of tracking the full wave field, we decided to track the energy that is localized over this particular length scale as a predictor. So we do that using a Gabor coefficient, or you can think of it as a wavelet coefficient. So what this wavelet coefficient does, it measures the energy localization over different regions of our domain. And actually it turns out that this is a great predictor because this is telling us the larger this is, the more sensitive the system is to give an extreme event in the near future. So how do we measure that? We compute this conditional probability. This conditional probability has as a condition this predictor, the value of the predictor, and what we predict is basically the expected maximum after t prediction, okay? So let's interpret this. What we basically see is that for small value of the predictor, all the probability, it's close to the average, right? And as we increase, as this value is getting larger and larger, you see that all the probability goes to very large events. Now this is important because we have managed with just one scalar to parameterize the expected value of the extreme events in the future without solving anything else. And this is a hard problem to do it statistically. It's hard to extract this sort of predictor. But there is an issue. And the issue is that for this problem, we more or less understand everything. Okay? The reason we were able to do this is because we designed the problem like that, right? The question is, if we are given a problem that we see extreme events and we know nothing about the dynamical mechanism, can we extract predictors like this? All right? So we go now to the real problem, and that is the Navier-Stokes equation. As I mentioned, we apply this external forcing. This is constant in time and acting over a given wave number. Kf is equal to 4 in this case. And this gives you a chaotic fluid flow. That's the dissipation function. Okay, that's the dissipation of energy over time. And you can see you have these spikes, these intermittent spikes. And the question is, can we find an initial state or a predictor that can tell us when these spikes will occur before they start to occur? Okay, that's what we're trying to solve. So the problem formulation, we consider our system state that lives in a given functional space. We have the governing equations. This is Navier-Stokes with the divergence-free condition and some initial state. And we set up, or we define, an observable, right? In this case, the observable is our energy input, which is more or less equal to the dissipation of energy. And our goal is to identify subspaces or modes that trigger extreme events. So what we are basically doing is we start with a very simple idea, right? We are interested to find states associated with extreme events in the future. So we characterize these states by the growth rate. So what we're basically trying to do is to identify the initial states associated with rapid growth over a finite horizon tau of an observable. This is an optimization problem as it is, okay? And one can solve it. If we want, we can solve it for really infinitesimal duration, and that will have an even more attractive form. But there is an issue with this optimization problem on its own, that it can lead us to solutions or initial states that are basically exotic, okay? They will never occur in practice. And this is how this whole thing came up. We were working on this problem, actually we were working on a nonlinear Schrödinger equation, and we were trying to find good predictors. And I discussed with a mathematician friend of mine and told me, what are you trying to prove for NLS? There are initial states that lead to unbounded solutions. What is your objective? The only problem is that these initial states that lead to unbounded solutions for NLS, they have such a nice chirp-like structure that they will never occur in the ocean. So they are there, they have rapid growth, but they're unrealistic, okay? So the question is, how do we make this realistic? Well, we supplement this optimization problem, that looks for states of rapid growth, with one additional constraint. We call it the feasibility constraint. And that is that this initial state must be on the attractor of the system, must satisfy some energy or probabilistic constraints. Okay? How do we characterize this constraint in practice? We will see that it's basically second-order statistics of the system. So we run some short simulation. We have some second-order statistics, enough, for example, to generate POD modes. Right? That gives us an idea of what is the shape of the attractor. And then we restrict our optimization on basically only solutions that live within this high probability region. All right, so it turns out that, if we take the infinitesimal time for the Kolmogorov flow, it's something that works very well. So we take tau, this growth time, we take this to 0, and then we end up with the supremum of an analytical quantity. So the instantaneous problem in this case, it has a nice reformulation, and it is, if it is continuous, which it is, it has also a solution. And in that sense, we have a well-posed optimization problem, which, and then we need to define the constraint, right? The constraint, as I said, it can be something really defined or basically formulated using energy quantity. So it can be a constraint on the energy of the mode or the entropy, depending. Or we may ask, which we'll do later for a more realistic turbulent flow, we will ask the mode or the initial state to satisfy some sort of spectral condition, to leave to be an initial state that satisfies a given spectrum, the spectrum of the attractor. So by imposing this condition, again, we exclude exotic unstable solutions. And for the Navier-Stokes problem, the whole thing takes a nice reformulation, which we solve using a Newton method. And here's the result. Okay, this is the growth rate. You see we have two suboptimal solutions. This is the black line. This is over the Reynolds, by the way. This is the black continuous and dashed line. These are suboptimal, and they basically correspond to some laminar unstable solutions that Kolmogorov flow has. But the interesting thing is that we find this additional branch here, the red one, that we find numerically, and this is associated with the mode that you see here. That, as we will see, it's actually the predictor. It's actually the precursor of extreme events. One thing I want you to notice is that this mode, it's quite robust as we increase the Reynolds number. As we increase the Reynolds number, the number of extreme events increase. And despite that, we have a pretty robust picture of what is the optimal mode in the sense I defined. So let's see how we predict the bursts with this approach. So what you will see, it's the dissipation function, which is basically the objective, the thing that undergoes extreme events, and the probability of extreme event basically defined using the projection of our current flow field on the modes that I just described. So initially, you see this is the vorticity field, the probability is 0, and then at this point, our predictor says that we have an upcoming extreme event, and you see, sure enough, right after we have an extreme event occurring. Because again, the predictor is able to identify the moment the instability is triggered. Okay? And right after that, we have the rapid growth. Okay? So in terms of numbers, what we basically apologize for the busy slide, but the rate of successful rejections and rate of successful predictions, which are the two important numbers that characterize the predictive capacity, they are pretty high, both of them, over 90%, depending on the Reynolds number. And the prediction time is set to 1 time unit, which basically corresponds to 2 to 3 eddy turnover times. Which is like, again, given the fact that we don't solve any equations here, we just measure the right observable, 3 eddy turnover times is a good number. Like the instability to develop, it's 1 eddy turnover time. So, of course, we can increase the prediction time, but that has a cost or an effect on the rate of successful rejections and rate of successful predictions. Okay, it goes down, as you can see here. So bursts of kinetic energy in channel flow, this is the next example or the next demonstration. We consider a more realistic situation of a turbulent channel flow. And here you see the Q criterion of the channel flow. This is the kinetic energy. And most of the time, this is the turbulent pattern that you see, and then over certain times we have laminarization of the fluid flow that you see here. This is followed by an increase of the kinetic energy, and then right after we have extreme dissipation of energy as the flow becomes turbulent again. And the question again is if we can find predictors that forecast, that can foresee the occurrence of such transition to a laminar flow. So we solve exactly the same problem I described before. We do it in a POD space of 30 modes. So we first do the POD analysis. We keep 30 modes. We impose the POD constraint. In other words, we are looking for initial states that live within this hyperellipse of POD modes. And then we're looking for the modes that have the most rapid growth within this domain. So by doing that, this is the initial state that we derived that is basically associated with very small wall stress and very small momentum, very close to the wall. And the next step is to just project our current state of the fluid flow on this particular mode and see if we can use this information to forecast an extreme event. And this is preliminary results, so we have not done a lot of processing on the movie. But that's the normalized projection, and this is the kinetic energy. You see it fluctuates around 0, and then at a certain point, at this point, we are sure that an extreme event will happen, and this is what you see from the growth of the kinetic energy. So you see how the predictor behaves versus the kinetic energy, and you see the associated Q criterion on the right. So again, what is the key? The key idea here is to look for states that have very rapid growth, but also they live within this attractor, the turbulent attractor of the flow. We have applied this framework. Actually, that was our initial motive to oceanic rock waves. And this is the equation. This is the Dyson equation for two-dimensional water waves. I explained the mechanism before. We basically have random superposition of waves due to dispersion. And we are interested to understand what wave groups are basically those that are more pronounced to an instability of the modulation type. So what you see on the right with respect to the length scale x and length scale y of the wave group and amplitude of a wave group, you see the probability of occurrence. So the colored surfaces are basically contours of the probability density function. This is just linear dynamics, right? This is just random superposition of waves. But there is this rock wave boundary that basically is telling you that if you have a wave group of these geometric characteristics, and it's above this surface, then in a deterministic manner, it will undergo an instability. So the question is, over this surface, which length scale is the most popular in the sense of probability for this thing to happen? We measure the scale, and then we just go and compute the energy localization over this scale. So I'm going to present you a one-dimensional demonstration. So yellow and green is basically wave groups with very low probability to undergo an extreme event, and red is basically wave groups with high probability. And this is periodic domain. We solve the equation I mentioned at the beginning, and you see that everything looks good, nothing dangerous in terms. And then all of a sudden, we have a wave group that is formed. By the eye norm, it doesn't look very suspicious in relation to the other waves. But at this point, we are 100% sure that this thing will give a rock wave in the future. Okay? And if we let it run for a while, then the instability develops, and we have a rock wave. All right? So again, what is the key? We're able to detect the instability the moment it just starts to happen, okay? And then we're able to measure this. So the key point is that what is the right thing to observe out of this infinite dimensional thing? What is the right observable in order to predict something else? So we have done this in an experimental setup. We basically measured, this is in a wave tank, collaboration with Professor Chapchub and Professor Onorato. So they provide us with data. They basically measured at the beginning of the wave tank, and this is the time series they provide. And they also measured, a few meters after, so they can confirm or disapprove the predictions we have. And so this is the data that we have from the first station, from the 0 station, the wave maker, and we predict that this wave group will basically evolve to a rock wave using the criteria. That involves basically just a wavelet coefficient, right? And sure enough, you can see that at the 5th station, a rock wave has formed and we're able to measure it. We have good percentage, definitely very accurate on capturing the rock waves. We have some false positives. Okay, and that may also have to do with the fact that we are not able to measure these rock waves because they may form between the measuring stations. So that's the first part. The second part is, all right, we have these precursors for extreme events. These precursors, they also provide some additional information. They also tell us which modes we should involve in a reduced order model in order to capture these extreme events, right? So these modes, they are not just precursors. They are also responsible for the formation of these extreme events. So the idea is to formulate reduced order models on these modes. So what we do, we consider the dynamical system, and we assume, without any loss of generality, that this dynamical system, it has a linear part, L of u, and then an essentially non-linear part, meaning with zero linearization, okay, denoted as H of u. So what we do, we decompose the solution on a subspace of modeled variables. Let's call them phi1 and the coefficients psi. And then they ignore variables which are phi2 and theta. And then we have some mean b that is an offset. So we can project the original dynamical systems exactly on this decomposition. So that will give us an equation for psi and also an equation for eta. Okay? In a standard POD approach, one will set eta to 0. We will completely ignore those, and we will have an equation for psi. All right? So if that is the case, then we will obtain an equation for psi. That's a very, very popular thing to do, and it's actually pretty effective, as long as this assumption implies that the role of eta is indeed small, because the energy of eta may be small, but that does not imply that the role of eta is small, as we will see, right? And this is a well-known thing. So because of that, people have tried to do different things. They have tried to add noise. That's the most popular thing to do, to add noise on the right-hand side, essentially trying to represent the effect of the ignored dynamics, okay? So we add noise and hope for the best. The only problem is that if we add noise, then uncertainty grows very, very fast and without a real reason. So we're trying to represent the ignored dynamics, and we are adding noise, and that creates uncertainty. Another approach, it's Takin's embedding theorem that is recently being used and highlighted. And what Takin's embedding theorem states is that under proper assumptions, ignored variables of the system, they can be represented in the form of memory, okay? So if you cannot observe or resolve certain degrees of freedom of the system, this effect can be essentially stated in very simple terms, right? That's not the way Takin's formulated the theorem, but in simple terms, you can represent the ignored variables through additional memory, okay? So the question is, so what Takin says is that this equation actually can be a very, very good approximation. The question is, how do you find this function involving delays? And this is where we're going to use data-driven methods, right? Nobody prohibits us from doing that with data-driven methods. In fact, people have done this in the past. But we're going to follow a different approach. And I will tell you what is the problem with this. You can do that, and it will work very well, except one case, the case where you don't have enough data. The problem with extreme events is that you don't have enough data. Okay? You have enough data for the main attractor, but not for the transitions. So what we're going to do to resolve this issue, we're basically going to consider, this is the exact equation, right? That's the projected part of the equation to the variables we are considering. And this G represents the interaction of the modeled modes with those that we ignore, eta. So what we're going to do is to use the equation-based reduced order model that is coming directly from projection with a data-driven complementary part. Okay, so this G, it represents only the effect of the modeled modes with the ignored modes. Essentially, it corrects this imperfect reduced order model. And it will be trained using the mismatch between the exact rate of change that is obtained through data and the ones that we get from the reduced order model. So we do that. We use a recurrent neural network, which basically it's an ideal candidate for this sort of thing. Recurrent neural networks, they involve memory inside them. And that's what we want to model, right? Through Takin's embedding theorem, we want to model memory. So I don't want to get into the technicalities of the recurrent neural network, but as I said, it's a situation where we have multiple hidden states that contain information over the past of the trajectory. And of course, this is a technique that can be easily adapted to a fully data-driven approach by just ignoring the reduced order model or set this reduced order model to 0. The only thing, the advantage is that it improves stability if we do this blended approach, and also it changes the model target distribution. What that means? It basically means that the distribution that you are aiming to learn, it's much easier. It looks much more Gaussian because it's the distribution of the mismatch, okay, between the perfect data and the imperfect model. The imperfect model actually has heavy tails, okay? So the target distribution, it's way more Gaussian and it's way more appropriate to be fed to this recurrent neural network. Recurrent neural nets, they have a hard time when it comes to extreme events. Okay, we start with a simple 6-dimensional Chernigov system. This is a 6-dimensional system. I don't want to get into it's a 6-dimensional ODE. The attractor of it, it consists by what they're called block states and zonal states. So it's a model that is coming from geophysics. It represents a barotropic flow. And x1, it's the variable that can tell you where you are, whether you are in the zonal regime or in the block regime. And this is how it looks like, right? x1 fluctuates most of the time around 0.9, and then there are these transitions that you observe in these pink regions. Okay, and the question is, if we can create a reduced order model that basically captures these transitions. So this is the original Chernigov. In another, it's in x1, x2 variables. This is the 5-mode reduction. Turns out that the 5-dimensional POD reduction, it contains 99% of the energy, but it has qualitatively completely different dynamics. Actually, it has a fixed point, globally attractive fixed point, so that's what you get from the 5-dimensional PO2 reduction. That's an important lesson, like to avoid or to be very careful to do reduction based on energy considerations. And this is the 5-mode plus this data-driven complement. And qualitatively, they look very good. But let's see in a more quantitative fashion. So this is the trajectory in the zonal flow. That's the regular regime, non-extreme events. And you see with black the exact time series for the 5 modes that we model. The blue is the blended approach that I just described you, and it has a very good match. Yellow, interestingly, it's the fully data-driven, okay? And you see that the fully data-driven, although it does well at the beginning, very fast it diverges, okay? And then the green, it's the reduced order model with just 5 modes, which we know it's a bad model. And this is for the extreme event. Again, we have a pretty good agreement between exact and the blended approach. And the yellow, which is the fully data-driven, without taking into account any sort of even imperfect dynamics, it has some divergence after some time. So we have applied, that's the RMS error, and I think this is more revealing. So the RMS error for the 5 modes, you see the big difference. This is the blue. The blue is the blended approach. And the yellow, it's the data-driven. Green is the POD, right? And you can see that there is actually a very important improvement as we move forward in time. So the message is that if you have an imperfect model, don't rush to do things fully data-driven. it may have some important information for you. It may be better to improve your imperfect model rather than starting everything in a fully data-driven fashion, okay? So models are important. And we go back to the Kolmogorov flow. Using the analysis I presented previously, we have this predictor mode that we derived. This predictor mode consists of three Fourier modes, okay? These Fourier modes, actually, they are not arbitrary. It's not an arbitrary thing that they turn out to formulate our predictor. These three modes, they formulate a triad that is actually resonating with the external forcing, and that's the dynamical reason why we get this extreme event. So these are the three modes that we're going to project to. So our aim now is to create a reduced order model consisting of just three modes for this flow, all right? And we're going to use the blended approach. The three modes, again, they are not randomly selected. They are selected using the criteria of a good predictor. So we know they're associated with extreme events. So what we see here, black is the truth, orange is the or yellow is the 5-mode POD reduction, which is pretty bad, as you can see. This is for the three modes, mode 04, mode 10, and mode 14, the three lines. Modulus, real part, and imaginary part, the three columns. So black is the truth, orange is the 5-mode reduction, and you see it does a pretty bad job. Green is the fully data-driven. It does excellent, except for the extreme events, right? So this is the green. Does not do very well during the pink region, the extreme event region. And the blue, this is the blended approach. And think of it, right? We are using, or we get this improvement by just utilizing a 3-mode reduced order model. This is a really bad model, okay, for a flow like this. This is the errors. This is the regular regime, error during the regular regime. Yellow is the 5-mode POD reduction. And green and blue, it's the data-driven and the fully data-driven. And basically, you see that during regular regimes, they are indistinguishable in terms of error. Nothing improves during the regular regime. But during the rare events, the blended approach does significantly better. This is the blue curve that you see here. All right, so to summarize, I have presented you two aspects involving extreme events. One is, how do I identify good precursors? How do I identify modes associated with extreme events that act as triggers of extreme events? And the basic idea is to formulate this as a maximum growth problem, but constrained on the attractor, okay? So that we end up with realistic states of realistic probability. And then we use these modes to formulate equation-assisted data-driven schemes where we utilize an imperfect model. This imperfect model, I'm emphasizing that it should have some physical relevance, right, with the extreme event. If it does not contain any information about the modes related to extreme events, then we cannot hope for anything. But if it does, then it has significant improvement. So I'll be very happy to answer any questions, and thank you very much for your attention.
Like that prediction of rogue waves, I was wondering if you have looked into the ringing of offshore platforms. Suddenly they are in steady state, and suddenly the amplitude increases, and it decays in a bell shape. You add damping, it doesn't make any difference. And I was wondering if your method could predict that also, because primarily it depends on the slope of the wave profile which is approaching the platform. And once that is detected, it goes into that particular mode. So this is just adding another dynamical system.
I don't think I understood the question. So can you elaborate what you mean?
Could you predict that?
The event after the rogue wave, basically the way it decays?
And it interacts with the body. Yeah.
I see. Well, this is a CFD problem, right? If you know that we are trying to predict when the rogue wave will occur. If we know that the rogue wave will occur, then we need to solve.
All spikes don't trigger that situation also.
That's an aspect that is very interesting. I don't know about that. This is interesting. Yes, that's something we should discuss. So you are saying that not all rogue waves lead to very high stresses on the structure. This is something interesting that, we should talk more. That's interesting, yes. Yes?
Can the rogue waves be produced in a lab? Can they be produced in
Right, yeah, that's what we have, so.
No computer, I mean.
No, that's, so the experiments I presented are basically lab experiments. So what we have here, this is a real lab experiment. This is in a wave tank of our collaborators. No, this is in Germany, actually. So these measurements were taken in Germany, and it's an interesting story, the way they did that, and why it took so many years, right? I mean, nonlinear Schrödinger solitons, they've been around for more than 40, 50 years, right? And people did that, actually, Chapchuk did that actually quite recently. The problem was that there was no enough, we didn't have a big enough wave tank because it takes a while for the instability, for the modulation instability to form. So what Amin did was basically did something very, very smart in my opinion. He used two wave makers and basically programmed them so that they simulate periodic boundary conditions. Okay, so they measure, from one side you measure the wave and you feed it to the other wave maker. And in this way you have basically an infinite length wave maker, and that created the rogue wave. Later they did it even without like a perfect, Stokes wave, but just an irregular background, irregular C state, and that gave.
So they can create any time they want in a short time. Now, how long it takes to create the circumstances? So this is.
For this sort of thing, it's order of, this is like order of seconds, so 16 seconds. Okay. In the ocean, it's a couple of minutes, 4 or 5 minutes, yes.
So I guess sometimes if you use even lower order PODs, the mismatch between the POD and the actual process can be even better captured by the recurrent neural network. So do you have any strategy on optimally determining the order of your POD?
No one has. This is more. the honest answer is that you have to try and see. Right? These sort of things, like there are no rigorous bounds on these things, especially when it comes to data-driven models. But qualitatively, what I can tell you is that by picking modes associated with a predictor, you have a higher chance to capture the relevant dynamics. And that's definitely not the case if you go for high energy modes. Okay? But on the other hand, you cannot ignore the high energy modes because this is the energy reservoir for the extreme event. So if you don't have the other mode somehow, here we do the recurrent neural net, then you don't have energy for these modes too. Other questions? Yes.
So if I understand correctly, everything that you've shown us focuses on predicting a specific sort of extreme event. Is that a correct understanding?
Extreme events that are associated with some sort of instability. So I will not be able to predict an extreme event in the context of waves that comes due to random superposition. Okay? In which case you have no dynamics. You basically have just random superposition. It can happen. It's within the Gaussian tail. Cannot tell you when this is going to happen. Okay? That's the honest answer. But that's why I did this informal distinction between rare events and extreme events. Yes?
So, for example, you cannot predict the next stock market crash.
I'm not expert in stock market anyways, but I guess in reality, I don't know whether there are any models that can tell us something, whether these are extreme events associated with some sort of instability. If it is, the first thing I would do is to take the time series and see the statistics. If they are really Gaussian, the answer is no. I cannot do anything. But if it's like heavy tail, that's an indication that there is some sort of dynamical mechanism involved with these black swans. And then we can start discussing about it. Yes?
One of your earlier plots when you were showing the time history and the PDFs, I was wondering why you have tails on both sides.
Oh, for the MMT model, I'm sure you mean. Let me see. For the MMT model, the way it is formulated, so that's the one you say, right? So for the MMT model, we are plotting, up there we're plotting the modulus. Here we're plotting the real part. It's a complex PDE. So it's basically symmetric with respect to the complex coefficients. That's not the case for water waves. Water waves, the equation I showed for water waves, they have asymmetry between positive maxima and between crests and troughs.
Even in the second order Stokes wave or third order, you end up in getting skewness.
That's why I'm saying this is not a water wave equation. This is weak turbulence.
The time history. If somebody gives me that time history, I'll have tails skewed on one side.
This is the modulus again, and that's the maximum. Yeah, that's the modulus of the thing. So it's a different thing. But it turns out that again, because of the way this is symmetric, you can actually see it. You can transform to u to minus u, and that will leave your equation invariant. You cannot do that with the other equation.
Well, let's thank our speaker.
Thank you.